Hello, in this video, we will learn about area moment of inertia, parallel axis theorem, and moment of inertia of composite areas, topics 10.1 to 10.4. Okay, so starting from here, topic 10.1, understand the concept of area moment of inertia, MOI, and determine the MOI for an area by integration. So let's first understand the word inertia. What is inertia? So inertia is a tendency of a body to resist motion or to resist bending or to resist angular acceleration. Now for chapter 10, there are two types of moment of inertia that we study. One of them is called area moment of inertia. Let's call this AMI, which is resistance of a two-dimension area to bending. So when we apply the force to bend something, to what extent that component will bend depends on the cross-section area and its moment of inertia. So that's called area moment of inertia. And the second type of moment of inertia that we'll study is called mass moment of inertia, which is resistance to angular acceleration. So if when we would like to rotate any component or any part, we need to apply torque or moment. Now, for the given torque or moment, at what angular speed the object will rotate depends on its area, so it depends on its the mass moment of inertia or MMI. So for this part of the video, we are talking about AMI only, that is area moment of inertia. The definition of area moment of inertia involves an integral of the form, and this is the correct equation, integral x squared dA, where if we have, and this is all, moment of inertia is always defined with respect to an axis. So let's say we have this like a simple shape here, which is located at distance x, the x from the vertical line, and we would like to calculate the moment of inertia, area moment of inertia of this shape about this vertical line, and this shape has area dA, then that can be calculated using this formula, integral x squared dA. And the unit for moment of inertia is nothing but the unit of this product. X is distance and it's x square, so it's meter square. Area is also meter square, so meter square multiplied by meter square, so it's meter to the power of 4. That is the correct unit. Applications. Many structural members like beams, columns have cross-sectional shapes such as I, H, and C, etc. Why do they usually not have solid rectangular, square, or circular cross-section areas? So if you see like in building construction, see these different cross sections or see this I section, these shapes are not like standard solid rectangular or circular shape, but they are defined in this particular way, like I, C, or J. And the reason is the one of the important property of the cross section area, that's called AMI, area moment of inertia. Now, moment of inertia or area moment of inertia is higher if majority of the area is being spread away from the axis of bending. So if this is axis of bending and if the area is farther away from axis of bending, then the moment of inertia is higher. In rectangular shape, majority of the area is concentrated closer to the center line, so its area moment of inertia is lower than I section. Now higher moment of inertia results in higher resistance to bending. So when they are used in construction and when the load is applied, they do not bend much if the moment of inertia is higher. And that's why we don't use solid rectangular, square, or circular cross section, but we use I section or T section, where or hollow section, where the material is farther away from cross section. So for this rectangle, if we replace that by a hollow rectangle such as this, as I have drawn here, where the material is only outskirt and inside part is hollow, then this particular shape has much higher moment of inertia than corresponding solid shape for the same area, for the same size of area. Let's say for both of these parts, if the area is like 100 millimeter to the 4 or 100 millimeter to the 4, this particular shape has higher resistance to bending than this. That's why you will see a lot of hollow structures in construction and manufacturing industries. So many structural members are made up of tubes rather than solid or squares and round. And why? The reason is this: the farther away the area is from the center line, higher will be the resistance to bending. Now, the general definition for okay, this is one more example. Let's say consider this beam RS where the load P is applied. Now, for the cross section of this beam, we have three different options: A, B, and C. They all have the same area, but considering the direction of the application of the load, I section has the highest resistance to bending because majority of the area is away from this center line. Compared to this is second most highest resistance to bending, and this has the lowest resistance to bending because majority of the area is close to the center line. So for moment of inertia, we would like to spread it away from the center line to have high resistance to bending. Okay, and that's being explained here. And yeah, these are the different formulas for, like, you don't need to memorize them here, they are just for example only. Now that is how the deflection, when the load is applied, the beam deflects, and this amount of deflection depends on moment of inertia. So the one that has higher moment of inertia will have less deflection. Now the formula for moment of inertia calculation is, let's consider that for this irregular shape, we consider a small square portion with area dA, which is located at x units from y-axis and y distance from x-axis, and in polar coordinates its air distance r from origin. So its area moment of inertia for this shape can be calculated using y square dA. So from x-axis, so see the distance from x-axis is y, so y square multiplied by area. That is called the x AMI. Y AMI is x square dA, and this is called polar moment of inertia relative to z-axis, which is r square dA. So in all of this three formula, the what is common is dA, that is area, multiplied by the square of the distance from the particular axis or point of interest. And to find the overall moment of inertia of this shape, we need to do integration over area. So it's integral of y square dA, it's integration over area. This is x square dA and this is r square dA. And the unit is inch to the power 4 or meter to the power 4. And now we can, I'll switch to notebook and explain you all the concepts. Now for standard shapes, the moment of inertia equations are predefined. So for example, and you will get this in the exam as well. So let's consider this rectangular shape, and C is the centroid of the rectangular shape. Its width is B and height is H. So area is B times H, and its moment of inertia or area moment of inertia or resistance to bending with respect to x-axis is 1 by 12 BH cube, and y with respect to y-axis it's 1 by 12 HB cube. So I-axis resistance to bending means if this is the shape and we try to bend it in this direction, okay, then about x-axis, then this is the area moment of inertia, and resistance to bending about y-axis is when we try to bend the whole shape about y-axis in this way particularly, then it's called area moment of inertia about y-axis, and it can be calculated using 1 by 12 HB cube. So be careful here, it's BH cube and this is HB cube. They are not the same formula. So you need to use the appropriate formula for this shape. Now, all the formula that we get into the data book or engineering like moment of inertia charts, this formula are actually defined relative to centroid, X is passing through the centroid. But what if we need to calculate the area, let's say this is H and this is B, so IX is 1 by 12 BH cube, okay, where x-axis is here and y-axis is here. So x moment of inertia, area moment of inertia is 1 by 12 BH cube if it's passing through centroid, if we try to bend the shape relative to an x-axis. But what if we try to bend the shape relative to an axis which is shown here, and that axis does not pass through centroid? So centroid is here, this is still like B, this is still H height, this is x-axis and this is x dash. So how can we calculate? And those two axes are parallel and the distance between them is d. So in that case, since both the axes are parallel, we can apply something called parallel axis theorem, where we first calculate the moment of inertia of the shape relative to x using the standard formula 1 by 12 bh cube. And then to calculate the moment of inertia relative to this new axis, we can apply parallel axis theorem that so this is called ix, by the way, this is called ix dash. So area moment of inertia of the shape about x dash is equal to ix plus area of the shape. So this area, cross section area, multiply by d square, where d is the distance between two axes. So this is the formula, and that's called parallel axis theorem. So for any shape, if we would like to calculate moment of inertia for about an axis other than the axis that passes through centroid, then we can apply parallel axis theorem. Okay. Now let's look at the another concept of composite shapes. This is very similar to what we discussed in chapter 9 for the composite shapes, that if we have a shape which is made up of simple standard shapes such as this plate with hole at the center, so the material is here only, there is no material at the center. So how can we calculate the area moment of inertia of this shape about x? So for that we can apply the concept of composite. So we can simplify this shape as made up of a square and circle, and since it's a hole, we need to subtract the moment of inertia of circle. So for this problem, if we would like to calculate the moment of inertia of the entire, like this shape, we need to calculate the moment of inertia of shape 1, which is ix1, 1 by 12 bh cube, minus we need to do ix2, which is moment of inertia of the circular shape, and that gives us the total moment of inertia of this shape. Okay, so that is called the concept of composite shapes. Now, since it is whole, we are subtracting. If there is a material which is added, then we have to do addition. So it's simple plus or minus in the equation of composites. But we can do that standard addition and subtraction only if the moment of inertia that we are calculating about an axis is in line or collinear with all three shapes. So x is common in all of them, so we can apply that equation. And y is also common like in all three shapes. So y of this shape, entire shape, is also same as the y of the square, and is also same as the y of the circular shape. We can still do that addition or subtraction. But if that's not the case, then we have to apply parallel axis theorem. So let's look at it. So for this T section, we would like to calculate the moment of inertia of the entire shape about x-axis. Now this can be considered as simplified as moment of inertia of shape 1 plus moment of inertia of shape 2, which is middle portion, plus moment of inertia of shape 3, which is the bottommost portion. Okay, so we can call this 1, 2, and 3. So this is ix1, this is ix2, and this is ix3. Now, since for the shape 1, the formula gives us moment of inertia about x1 axis which passes through its center. For shape 2, it gives us formula about x2, and for shape 3, it gives we know the equation about x3. So we can calculate ix1 as 1 by 12 bh cube, which is this b here, and h cube is this height. However, this is only about ix1, but if we are interested to calculate the overall moment, like moment of inertia of top rectangle only about ix, then we have to apply parallel axis theorem. So ix for shape 1, you know what, we can, let's call this x dash for now. So ix dash, so we are defining the main axis as x dash. So ix dash is equal to ix1 plus ad square, where d is, or we can call this d1, where d1 is the distance between two parallel axes here. So that will give us ix1 dash, that is moment of inertia of shape 1 about x dash axis. Now same thing we can apply to shape 3. So ix3 relative to x dash axis can be calculated as ix3, that is moment of inertia of this shape only about x3 plus a d2 square, where d2 is this distance. And finally, for the middle shape, ix2 dash is 1 by 12 bh cube for that shape. So this shape. Now, for that shape, we do not need to apply parallel axis theorem because the x-axis or passes through the centroid of that shape. X dash axis passes through the centroid of the shape. So we are all set. But x1 and x3, they do not pass through centroid of the middle shape or x dash axis. So we have to apply parallel axis theorem. So now the total moment of inertia of the I section is ix1 dash plus ix2 dash plus ix3 dash, and that gives us the overall moment of inertia. So we cannot simply add ix1 and like we cannot simply add this and this with the middle portion, but we have to apply parallel axis theorem. So we need to do these two more steps and then substitute their value into the final equation to get the moment of inertia of the shape. We will do one problem in the next like video, so that will make everything very clear. And now finally the concept of radius of gyration. This is very useful concept. So let's say we have this area and we would like to calculate the moment of inertia of this area about x-axis. We can apply the formula Ix is equal to 1 by 12 bh cube. But we using radius of gyration, what we can do is we can simplify this entire like two-dimension area as a point area. So it's a very small like point mass that has the same area as this rectangle. So whatever is area of this rectangle is the same area, but then that means it will have the same moment of inertia about this axis. Then it has to be located at distance kx from that axis. That kx is called radius of gyration. And the formula for radius of gyration is Ix is equal to kx square times a. So if we need to find out the radius of gyration for this shape about x-axis, we need to first find the area, we need to find the moment of inertia, and then we can find out kx using this equation Ix divided by a, square root of that, because this is square here. So this is called radius of gyration. Radius of gyration has the unit either meters or inches, and its physical significance is that it lets us simplify the engineering design by considering whatever shape we have as a point area that has the same magnitude as the total area and that has the same moment of inertia as the total moment of inertia of this shape. Okay, so these are the concepts, and then now we will solve one problem in the next video.